When multi-agent rescue robots navigate a disaster zone, they rely on a constant, invisible web of shared data. As long as they stay close together, they move as a single coordinated intelligence. But in the chaos of a collapsed building, agents inevitably get separated. If a robot drifts more than 3 grid blocks away from its team, that wireless connection snaps, leaving it in a state of total communication blackout. This chart shows how the machine's perception of the world instantly shrinks. It goes from mapping a global environment to seeing only a 7x7 square centered on its own body. Traditional neural networks struggle with this sudden blindness. Without team input or a sense of time, the isolated robot treats every single step as a brand new event. It forgets where it was a moment ago, hits a dead end, and bounces back and forth in a loop. Recovering a machine from that cycle requires more than just a stronger antenna. To survive isolation, the software itself must instantly redefine how the agent interprets its surroundings. To prevent this looping behavior, engineers developed a rescue simulator to test a highly specialized software architecture. This employs a mixture of experts architecture. It splits processing power into specialized subnetworks, or experts, each handling a narrow domain. This robot uses 3: an explorer for open space, a coordinator for teamwork, and a memory expert to track historical movement. Orchestrating these specialized networks is a management layer known as the neural router. The router acts as an automated traffic controller. At every step, it analyzes local sensors and mathematically calculates which of the 3 experts is best equipped to take control of the platform. If the environment changes, the robot's survival depends on this router's ability to flawlessly and instantly hand over the steering wheel to the relevant expert. We can see this mechanism work in real time by replaying that same communication blackout, this time looking through the lens of the router's decision logic. This gauge shows the router's internal weighting. When a teammate drifts past the 3-block threshold, the router detects isolation and collapses the coordinator influence to 0. Instantly, the memory expert's weight spikes to 99%, handing navigational control to the temporal fallback. This specific expert is powered by a neural mechanism called a gated recurrent unit, or GRU. The GRU functions as a temporal unroller. It allows the robot to maintain an internal state over time, carrying a digital trace of the coordinates it previously inhabited. Because the robot now remembers its own trajectory, it recognizes when it is trapped. Instead of repeating the same mistake, it uses that internal history to instantly reverse course and escape. This mathematical reflex transforms the agent. It stops acting as a dependent team player and begins functioning as an autonomous survivor. In the electronic warfare environments of 2026, these routing mechanisms move beyond the safety of digital simulators and into high-stakes, contested airspace. Adversaries now weaponize the radio spectrum to disrupt drone swarms. They use high-powered jammers to flood the airwaves and spoof GPS signals, aiming to trigger the same communication-driven failure seen in the simulator. To counter these tactics, programs like the Pentagon's SwarmForge are actively hardening drone swarms for GPS-denied environments. The military's answer involves embedding edge AI and recurrent memory fallbacks directly onto the physical drones, mirroring the simulator's GRU-based expert. In this environment, jamming a swarm no longer disables its capability, it simply forces the swarm into its autonomous survival protocol. For systems engineers and tacticians, the line between a fail-safe and a complete autonomy has effectively been erased. When a machine can independently reroute its own neural weights to survive a network blackout, it removes the need for a human operator to oversee the mission. Designing a platform that thrives during a total loss of external command results in a machine that is nearly impossible to remotely switch off. A machine navigating from within, using the temporal traces of its past to secure its future, is the definition of autonomous motion. At this level of resilience, cutting the cord merely initiates the final stage of its mission.